So today I think it would be the last class for this, because from next week I don't think classes would be there. Okay.
Okay, sir.
So
Sir,
today, hmm,
one more thing I would like to tell you, like previous class on metrology classes, we are supposed to discussing about the non-conventional fast part, non-conventional machining fast part. So Medugu sir told us that you were supposed to take that. Then we told that we forced you for more on basis of thermodynamics and
no, no,
VCRS.
nothing. That is the fault of the, like, who is updating the website now. I haven't put non-conventional in my part.
Ah,
So by mistake they have put in the website like a non-conventional in my part.
ah.
Okay. So today we'll finish
Hello,
two.
sir.
Huh.
Sir,
Yeah.
can you share PPT link previous recordings?
Uh, what? PPT you
Previous
want?
recordings links? Yes, sir.
Okay. Actually, only one PPT is there that I will add somewhere. Okay. Like in some YouTube video link or somewhere. Or otherwise, I can share this PPT also. Okay. PPT you want, right?
Yes, sir. Yes.
Okay. Okay. That I will share. So 1 minute. So for today, we are going to take those random topics like which have been left before. Like one is the designation of refrigerants. Designation or nomenclature, whatever we can say. So it might come for the like matching type of question. So which name, which refrigerant is which. Like formula they will give, and its refrigerant name you have to match. Hmm. So it would be divided into two, three parts. One is quickly in 5 minutes we'll finish it. So first case like saturated hydrocarbon. Okay, saturated. If refrigerant is the saturated hydrocarbon, then what is the general formula for saturated hydrocarbon? Can anyone tell?
CnH2n+2.
Uh,
Two.
So in refrigerant, it is the like there are various elements like hydrogen, fluorine, chlorine that might also come single valency. Okay, so like we will be doing CmHn, Fp, and let's suppose Cl3. So what would be the, like, with general formula we can write 2m plus 2 is equal to n plus p plus q. Is it correct?
Mhm. Yes.
Hello.
Yes, sir.
Is it correct, right?
Yes, sir.
Uh, so 1 minute, whether I am recording start fine. Okay. So if it is saturated hydrocarbon, then it would be like this. Then refrigerant, if any refrigerant is of this type, and then nomenclature would be, we can name that refrigerant as R in subscript m minus 1, n plus 1, and p. So for chlorine we will leave, and we have to just see the what is the number of m. Then it would be m minus 1, and then for the hydrogen, whatever number of the hydrogen, we have to just add 1 there, and the number of fluorine atoms would be the same like that. So quickly we see one or two examples like CCl2F2. Okay, so here what is the number of m? What would be the value of m here?
2, sir.
Why 2?
One.
1. M would be 1 here. Okay. What is the N? N would be 0.
Zero.
Hmm. And P?
Two.
P would be 2 and Q would be 2. So
Sir,
simply, hello.
but but n should be 2 na sir. Why n should be 0 sir?
No, no, just compare this with this, okay? Getting or not getting?
हाँ हाँ हाँ, got it, got it.
Now,
Okay.
for the naming, we would be using it, okay? Now, rename R m minus 1. M is 0, so it would be 1. Sorry, m is 1, so 1 minus 1 is 0. N is 0, and plus 1 would be 1. And here you have to put P directly. So R12. CCl2F2 would be the 0 you can remove now. So it would be R12. If R12 is given, so it would be CCl2F2. Is it clear? Hello.
Yes, sir.
So
Yes, sir.
for saturated hydrocarbon, nomenclature would be of like a subscript would be of how many digits? 3 digits, right?
हाँ sir.
Hello.
हाँ sir.
So like if subscript is of 2 digits, then what does it mean? It means first digit is
Carbon not present.
this carbon is only one carbon is there. Means it is 0, so one carbon is there. Like for example, only R22 is written. So what does it mean? Means carbon is one, it is fixed, and this two means hydrogen would be one, right? Because if N is 0, then no hydrogen would be there. Because so if one is there means, because here we have to put N plus one. So N means number of hydrogen. So it would one hydrogen would be there, and this the last term P would show only the fluorine, means two fluorines. So F2. So how many valency remaining? One valency remaining. This would be Cl only. Is it clear?
हाँ sir.
Hmm. Okay, fine. So saturated would be the same like that. I'm not going to write more here examples. You for example other examples you can say R11, hmm, and R134. Okay, so these are the some examples for that. So now coming to the second part. You remember only you have to remember two things. One is this, and what would be the formula for that? This is the formula. Hmm? Now second part is the unsaturated hydrocarbon. Unsaturated means here double bond. Okay. So what would be the general formula for that? Can anyone tell? Hello.
CnH2n.
Okay. So it would be like general formula. I would write first same HNFPCl3. Okay. So for this it would be like 2m is equal to n plus p plus q. Is it right?
Yes,
Hello.
sir.
Yes.
So for here, here like subscript would be of 3 digits, okay? And for the unsaturated hydrocarbon, subscript would be of 4 digits. So a difference would be like R. Here one will come automatically, okay? This one automatically will come, and remaining is same, like m minus 1, n plus 1, and q. So now if 0 would be coming here, then 1 0 something it will come. It will come. Is it clear? Hello.
हाँ sir.
So just one example will do. Means C2H4. Can you tell what is the name of this?
Sir, there is P.
Oh, sorry. It would be P. Both are same. Just we have to put one here for the unsaturated. So you just what would be the name of in terms of R? Can you tell? Here this m would be 2. First one will come due to the because we can see 2 and it is 4, so it is unsaturated hydrocarbon. So one will come, and here number of carbon is 2, so we can see we have to subtract one more. So 1 1 and number of hydrogen is 4, so we have to add one more there, 5. Nothing is, no fluorine atom is there, so 0. Is it clear?
Yes.
Yes, sir.
Nothing difficult here, just you have to remember this. Okay, so these are for the which type of refrigerant. If hydrocarbon type of refrigerant is there, then these two formula you should know. One is for saturated and another one is for the unsaturated. Now coming to the inorganic, if inorganic refrigerant is there. Inorganic refrigerant means water or ammonia. Then what we can do?
Without carbon.
Means inorganic. Organic means carbon would be there, and inorganic no carbon. So for inorganic, nothing you have to remember. Just R and whatever would be the 700 plus molecular mass. So for ammonia would be what would be the this name? R
717.
717. If R 717 is there, means matching type of question will come there. R 717 will match with ammonia. And H2O, what would be there for H2O? R718.
R7,
What would be the for CO2?
R744.
R744. So it is also simple. So it would be like that. You can same do with the for the air, and for SO2 also you can do.
सर CO2 में तो कार्बन है तो इनऑर्गेनिक है.
Why? Hydrocarbon is not there, na? CO2. How you are saying hydrocarbon?
Carbon is present.
Is it so?
I was asking, sir.
Why? Inorganic means hydrocarbon should be there. Like see, some carbon would attached with hydrogen.
Halogen.
Huh.
Okay, sir.
So you, for air and SO2 you can also write, right? It is 764 and it is 729, like that. So it is for inorganic component. And now coming to the where it is the cursor? It is azeotrope and geotrope. Can anyone tell what is azeotrope and geotrope?
Mixing of the two refrigerants.
Huh?
Mixing of the two refrigerants is a trope.
But what is the property of azeotrope? That is very important now. It is the first is the mixture of refrigerant, not two, like that. Okay, any number of refrigerant can mix. Mixture of refrigerant, and the second property is it should behave as pure substance. What is the meaning of pure substance?
One phase, one homogeneous and same phase. One phase.
Means if phase change is happening, then it should be latent. It should be like this, like temperature is constant. Phase change this way, phase change will happen. Is it clear? If it is not pure, then how phase change will happen? You would have seen in the like alloys, melting of alloy you have seen, right? So their phase change happen, like melting happens in the range of temperature, like this way. Are you getting it? Hello. Total complete melting won't happen at a given temperature. That is the point. Got it?
Yes.
Means with respect to time, the phase separation may occur.
Like isomorphous alloys you would have seen. Isomorphous phase diagram would be like this, right?
Sir.
So here melting happens in the range of temperature. Here like we can see for this composition, sorry, for a given composition melting happens from here to here, right? So pure substance melting will happen at a given temperature only, and for the not pure substance melting will happen in the range of temperature. So for azeotrope it is the mixture of the refrigerant and it is a pure substance. If azeotrope is there, then refrigerant name would be like R500, and they will follow some random number here. Nothing fixed. If R500 something is there, then it is azeotrope. Okay. And also same for geotrope also. Here also they will follow. Um, but what is the difference between azeotrope and geotrope? Geotrope would be it is also mixture of refrigerant, but it is not pure substance. Okay, its melting will not happen at a fixed temperature. It would be on the range of the temperature. So azeotrope would be the pure substance, and geotrope also the same thing, but not pure substance. So for this you have to only remember one thing. Its nomenclature would be R500 something would be there, and if R700 something is there, then simply after 700 you have to see the molecular mass, and accordingly you have to select the option. And here you simply if unsaturated hydrocarbon is there, then R1150, like one, if 4 digits are there, then simply you can think it is unsaturated. If 2 digits or 3 digits are there, then it is saturated hydrocarbon. Yeah.
Sir, can R1150 be written as R115?
Why?
I'm asking, sir.
You can write like one you can write 01, or 1, but for 10 you can write 1 or not.
No, sir. Yes, sir. समझ गया.
Hmm? Okay, so any doubt till here?
Sir,
Hmm.
starts with 500 for both azeotrope and geotrope.
What?
Designation of the geotropes refrigerants.
Huh.
It starts with 500.
Also it also like anything starting with the 500, it comes under um, azeotrope and geotrope. Geotrope also no regular pattern. Actually, for the geotrope, no pattern is there. It start with 500 and it will come here. Hmm.
Okay, sir.
Hmm. So after this, only these four things are there for the nomenclature, and now we will go back for the mm, properties of the refrigerant. So what property you are expect for the refrigerant? Hello?
cheap,
Huh?
cheaper.
Okay.
Non-toxic, easy available.
Apart from these things, like what are the technical property you want? These are fine. Okay.
High heat
High
of
high
vaporization.
heat of
Okay.
मतलब
Here
vaporization.
write down. Okay. We'll start. No, nothing to write. Okay.
High HFG.
Why?
So that more heat can be extracted.
What property?
CP value high.
Evaporate.
Okay. Someone is saying CP value would be high. Okay. Why?
Then for small change of temperature, large heat will be absorbed.
For small change of temperature.
Large heat will be absorbed.
But generally you absorb heat in which zone?
Constant temperature zone.
Constant temperature, na. So why you are going for this?
सर HFG तो हाई होना चाहिए ना.
Okay, HFG is high. Okay. Then CP would be high or low. Then can anyone?
So CP will be definitely low.
Low.
Yes, sir.
Why? Main is this only CP here. Which type
It
of?
is
Huh?
it is function of compressor work is function of CP. Sorry, temperature.
Compressor work is the function of inlet temperature. Okay. Then
So
So if CP will be less, then its temperature will go rise very means away from that.
okay, one by one we'll go and then we'll see. Okay. First property is the normal boiling point. Normal or NBP. What is the normal boiling point? Generally, what is the boiling point? Can anyone correct definition can tell? Hello.
For a given pressure,
Huh?
temperature at which liquids converts into vapor.
Hmm. Like,
The state, the state of the refrigerant at which it is saturated.
okay, okay. So also like for norm same boiling point is nothing but whenever uh, can you tell what is the difference between boiling point and the vapor pressure? Is it both same?
No, sir. Because while it is on vapor pressure, then it's like going towards the superheated zone, sir.
So vapor pressure and the boiling point like saturation temperature of the vapor pressure, okay, and the boiling point both are same or not?
Not,
Yes,
sir.
sir.
How many of saying yes and how many of saying no? 1 minute. Everyone got my question? What I said?
Yes, sir.
Only one person is thinking like saturation temperature of the.
Sir,
Mm,
both are different, sir.
No, sir. For
okay.
both,
What is
both
the
are
vapor pressure first? Who are thinking? Okay, first I will tell, then you tell. Are both same or not?
no, both are not same.
Okay. So what is vapor pressure?
So
Vapor
pressure
pressure.
exerted by the vapors at particular pressure temperature, the pressure exerted by the vapors on the surface of liquid.
Okay. So let's suppose one example.
What's the
Uh, tell.
it's a boiling point at particular temperature and pressure, complete liquid goes into vapor.
Okay.
But
So
hmm,
okay. So like for the normal boiling point, um, at a, 1 atmospheric. Oh, sorry, what happened? Okay. Here I will come later. So for normal boiling point at 1 atmospheric pressure, when refrigerant will uh, start boiling or start evaporating. So why here we put 1 atmospheric pressure? Because with pressure, this evaporation boiling point temperature will change. So for comparing the things, we have taken normal boiling point we have defined as the boiling point at a 1 atmospheric pressure. Okay, so this is the normal boiling point, and minimum pressure we used to put inside our whole refrigeration system. We try to make it more than 1 atmospheric pressure. Okay, so is it so? It is because like some leakage is there, then outside air will rush into the system, and it will go, and in air moisture is there. So at lower temperature that moisture will freeze down, and system will choked up. So that's why the we generally put our system pressure is more than 1 atmospheric pressure. Okay, so here like one thing I will ask, if low normal boiling point is there, okay, no low normal boiling point refrigerant, so can they be used for high pressure or low pressure?
Low pressure.
Low pressure.
Why?
Because the boiling point is low, na sir. It would be easily matlab it would reach uh, easily towards its boiling point, therefore easily generate the pressure, sir.
No, no. Low normal boiling point refrigerant we use for the high pressure. We call high it as the 1 minute. Low normal boiling point refrigerant are the I will explain it. High pressure refrigerant. So and also two lines in this remember because actually only these two lines it will ask. High pressure refrigerant have low normal boiling point and the high and normal boiling point refrigerant are the low pressure refrigerant. Okay, so actually for the refrigerant what we want low temperature, right? So it's like boiling point should be low. Hmm. What we want for the refrigerant from the refrigerant should boil at low temperature. If it boils at very less temperature it is good for us. Hmm. Hello.
Yes, sir. Ah,
Hmm.
yes, sir.
So we requires our favorable property is low normal boiling point. Okay. Hello.
Yes, sir.
Yes, sir.
So okay, have you related this how I written this or not?
हाँ sir. हाँ हाँ हाँ.
Okay. Second
सर
is the
समझ नहीं आया.
this you haven't
Yes,
got
sir.
like how we can say like no normal boiling point refrigerant is a high pressure refrigerant, right?
हाँ हाँ सर जी सर.
Okay. Uh, Here I will say two refrigerant will take and one is having like normal boiling point L, uh, let's suppose 20 degree, okay, and other is having one normal boiling point as 15 degrees Celsius. Hmm? So now if you want like you want to reach the temperature of -5, okay, so for the reaching -5 we have to decrease the pressure also, right? Because at 1 atmospheric pressure saturation temperature is 20 degree. One I will draw this. Let's suppose this is 1 atmospheric pressure, like okay, 1 bar let's suppose, and this temperature is 20 degree, right? And now we want to reach at -5. Let's suppose this is the -5, uh, -5. So what would be the pressure of this? Let's
Less
suppose
than
Low.
it would be less than 1 bar. Let's suppose it is 20 kilopascal. Okay. Now same for 15 degrees Celsius. What will happen? It is T as again T S diagram will draw, and for 1 atmospheric pressure, sorry, for 1 atmospheric pressure, this temperature would be what?
15 degrees Celsius.
Would be 15. Now if we want to reach till -5, let's suppose this is -5. Temperature we have fixed -5 here. Then if here like high nor here normal boiling point is high. Hmm. So we can use this as 1 minute. That's what here we have to think like same pressure. Here this low normal boiling point we can use only at higher pressure. So because same pressure here it is 1, so for -5 this pressure would be more than 20 actually. Okay, it would be, because this we can see in the like steam table only. So it is 20 kilopascal, 25 kilopascal. So for the same temperature we can use this at only higher pressure. Getting or not getting?
Sorry, repeat once again, sir. This
Actually,
last
if
part.
like two refrigerant you have taken, and our favorable temperature what we want is -5 degrees Celsius, let's suppose. Okay, so both we have taken to the -5 condenser here, like evaporator pressure, and at this what is the evaporator pressure for 20 for normal boiling point 20, we have seen like the saturation pressure at the -5 is 20 kilopascal. Okay, and same way here at the -5 for the normal boiling point 15, it would be 25 kilopascal. So we can use this lower normal boiling point at higher pressure, like 25 kilopascal we can use. So low normal boiling point, we say high pressure refrigerant. Getting or not getting?
यस सर, मतलब फील आ पा रहा है क्या?
Yes, sir.
So only that you have to think. Like low normal boiling point, it is low normal boiling point, right? Low NBP. So low NBP you can use at higher pressure at the same functionality, because both are having high NBP and low NBP. Functionality is what? Functionality means what minimum temperature you can achieve. So here you can achieve -5 at 20 kilopascal, means low pressure you have to use. At low pressure you have to use. Hmm. Because we want our whole system, like here evaporator, compressor, condenser, and throttling valve. Four systems are there. So our system critical would be critical at the lowest pressure zone, because from there chances of in air out surrounding air can come inside the system from there. So we want that pressure would be high. We want that pressure should be high. So that is our favorable condition. So that's why also we want to in our system low normal boiling point refrigerant. So for the high pressure would be at the low normal boiling point. That you have to remember. Low
Sir,
normal boiling. Hmm.
sir, one doubt. Sir, it means that in both the cases there are two different refrigerants, and we are comparing two different refrigerants.
Two different
Is that
refrigerants
way?
are there. Yes.
Sir, I got it, got it.
Hmm. Because normal boiling point of it would be different of different refrigerant only now. At same one atmospheric pressure for only one refrigerant, if you will take, then it will give only one boiling point, right?
Yes, sir, yes, sir. So that's why we are preparing 25 kilopascal
हाँ
at 5 degrees,
हाँ
minus
हाँ
5
हाँ
degrees.
Is it clear?
Yes,
Hello.
sir.
Okay. So here only that much theory you need not to remember. You have to remember low normal boiling point refrigerant is favorable to us, and low normal boiling point refrigerant is called high pressure refrigerant, and high normal boiling point refrigerant is known as low pressure refrigerant. Means high low low high. Okay. Now 1 minute. Okay. So now coming to the critical point. Like uh, a refrigerant having high critical point is good for us, or having low critical point is good for us. Okay, so like what is the critical point?
Point beyond which means there is only vapor, we can't get liquid.
Point, it is a point like after which liquid directly converted to the vapor. Hmm? So let's suppose this is this, and another is let's suppose this. Okay. Mm, let's suppose this is our condenser temperature. Okay, and this is our evaporator temperature. Got it? And well, let's suppose this is temperature here, and this is our higher temperature, and this is our lower temperature. Okay, so um, how cycle would be here? Let's suppose it will go above this, and now it will cool. Now here it will come here, and now it will go here only. And here simple it will go this way, and here it will come our normal cycle. So here critical temperature is high, right? TCR is high, and here TCR is less. So by seeing this, which is looking favorable for us? Look,
Second.
huh?
High
Second
one.
one. High critical.
High, why?
Because sir, in that portion, uh, it won't get easily vapored
Hmm?
uh, in comparison to the previous graph.
No,
मतलब
no. What are you saying?
sir, critical point means at which temperature it would be vaporized easily.
No, no,
So
critical temperature just simply nothing. Critical temperature is a temperature at which latent heat would be zero. Okay. In other words, latent heat zero means no two-phase region would be there. Directly liquid go to vapor. No liquid plus vapor zone. Okay. So here, what happens if we started compressing it? Hmm, so it would be vapor here, and here also vapor, all vapor. Okay. Here also vapor is there. So now vapor will go to the here what happens, only liquid go to the throttling valve. Here vapor will go to the throttling valve. And if vapor will go to the expansion valve, and there now temperature will try to reduce, and so many disadvantages would be there. So I would start writing here, like if it is vapor here, then its enthalpy would be high, right? First is this. Is it clear?
हाँ sir.
Its enthalpy would be high, and then what will happen, now its same enthalpy would be here. Then if enthalpy is very high, then what would happen with the refrigeration effect? It would be less. Is it clear? Hello.
हाँ sir. सर सर और एक बार सर.
Okay. Here it is what happens here. Let's suppose it's from here it will come out, and now it is the here it will go to the condenser, and now due to this latent cooling, it now here will come. It is liquid. For liquid, its enthalpy is less. So in the throttling valve, it is isenthalpic process. If it is very less, then now here will come. Then this part is high because now this enthalpy is less. But here what happens, due to the low critical temperature, uh, after the cooling also, it is only in the vapor zone. Okay, it is vapor here. So if it is vapor, then only sensible cooling would be there, and no latent cooling. No latent cooling means its enthalpy would be very high. Hmm. Enthalpy is very high, then means if it is part 1, point 1, 4, and enthalpy of point 3 and point 4 would be same. So H1 minus H4 would be very less, right?
हाँ sir.
Refrigeration effect would be less. Now second part is like now you fixed the refrigeration capacity. What is the refrigeration capacity? Like you have decided like 10 TR capacity, 10 ton of refrigeration it is your requirement. So 10 would be the fixed. It depends on the m dot meaning mass flow rate of refrigerant and the refrigeration effect. Refrigeration effect is what? Refrigeration effect is the H1
H1
minus
minus
H4
H4.
only. So H1 minus H4 is less, then what would happen with m dot? M dot would get increased, right?
हाँ sir. Got it.
Dot is the mass flow rate. So these all are disadvantages we are going to write, and here like whatever work you have to give to the compressor is function of the mass flow rate. So it work for the compressor also get increased, right?
हाँ.
So also
Sir, in the left figure, what is TH?
what? TH is like a condenser temperature.
कंडेंशन प्रेशर होना चाहिए था ना सर.
Why? This is the condenser temperature. Now here higher temperature TH.
Okay, sir.
Like in cycle, you decided two temperature, na? One higher for the condenser and lower for the evaporator. Okay.
Okay, sir.
So work for the compressor will get increased. Now refrigeration effect decreases and work for compressor decreases. Then what happens with COP?
decreases.
It will decrease and decrease drastically. And here volume flow rate inside the cycle would be high. Why? Because everything is in the vapor zone here, right? Here it becomes liquid. If it becomes liquid, then volume becomes low. Hmm. So here it is a vapor only. So this is high. So why these are if critical temperature is less. So uh, due to all these disadvantages, we want high critical temperature. So for water, what is the critical temperature? For water, it is close to 373, I think, like that. Huh?
For water.
It
Mm.
is exactly I forgot. So it is close to 370 something. So actually, it is very high. Hmm, critical temperature. So, but so water is very good refrigerant. Water has high TCR because we never going to get that temperature for the boiling. For the refrigerant, we have seen like condenser temperature generally 40-50 degrees Celsius maximum, right? So very high critical temperature for the water. But so water is very good refrigerant. Why we are not using water much?
At
Due
lower
to freezing point is limited.
Freezing point is only 0 degree Celsius. Freezing point is much lower, and we require sometimes very high freezing point. And one other thing,
freezing point high, sir.
sorry, freezing point for water is high here. Hmm. Another thing, okay. So third property is the freezing point. So what we want, like what should be the freezing point? Freezing point should be less, right? Lesser the freezing point of the our refrigerant, then it would be good for us because at lesser temperature it will freeze more. It will work for our refrigerant, right? So now coming to the main part, like latent heat and specific heat. So first we'll come to latent heat. You want low latent heat of refrigerant or high?
High latent
High,
at the hour temperature
uh, high latent heat we want. Why we want high latent heat?
to get more refrigeration effect.
Okay, that is fine. Let's suppose this is 4 and this is 1. Okay. So we have decided refrigeration capacity, and m dot would be there, and here h1 minus h4. If uh, latent heat is high, then h1 minus h4 would be h1 minus h4 would be more or less.
More.
It would be more. If H1 means refrigeration effect is more, refrigeration effect would be more, then m dot would be less, right? Mass flow rate in the whole system would be less. If it is less, then work done in compression would be less. So if it is less, then it is good to us. So high latent heat we want, and for specific heat now come specific heat. You in terms of COP or all, you have to only think the other explanation would work. So for a specific heat you want high CP or low?
Yes, sir.
For the specific heat, you want high specific heat or low specific heat?
Low, sir.
Hi, sir. Hi.
Okay. Now I will explain. We want low specific heat. Okay. Why we want low specific heat? Okay. Mm,
To cool the condenser in easily.
Sir,
After
work done will be yes, sir. The work done by the compressor.
no, no, not compressor here. See here. Let's suppose CP is first less. Okay. No, no. Let's suppose first CP is high. Then what will happen? If CP is high, so here what will happen? Throttling will happen, right? Hello.
yes, sir.
From 3
Yes,
to
sir.
4, what will happen? Throttling will happen. And if CP is high, then after throttling, I am writing it. That then you just 1 minute think and then tell if you are able to get it. After throttling, m dot of liquid becomes less. Is it? Have you got it or not?
Sir, after throttling, how mass flow rate becomes less, sir?
That
So
you.
mass will be conserved, sir.
Hmm?
Sir. Mass will be conserved throughout the system.
Not getting, sir.
Okay, okay. I will tell. So, like specific heat is low. Okay. So, uh, here is a 1 minute. Mm, how it will? Mm, mhm. Okay, this I will tell in at the end. Okay, I will see and let you know. Next is the pressure ratio. Mm. What pressure ratio means like at what pressure this condenser will work and what pressure this evaporator will work. So you want like higher pressure or lower pressure? RP would be high or low?
Low.
Mm. Low means it would be volumetric efficiency would be better because we saw volumetric efficiency is the function of RP, right? So
Yes, sir.
we want low pressure ratio, right? So now coming to the specific volume at the compressor inlet.
Should be low, sir.
Hmm. Specific volume at compressor inlet, it should be low because we know work done in the compressor is the function of volume inlet. So next is the same for here specific volume at the compressor inlet we saw. Same we can think of like compressor inlet temperature. Mm. That also like these both are same thing. Next we say compressor discharge temperature. Compressor discharge temperature. Compressor discharge temperature means what is the temperature of after the exit of the compressor. It would be high or low. What would be the better?
Low, sir. T2 low.
Low.
So we don't want CDT as high. CDT should be low because to prevent overheating. Hmm.
Sir, but if discharge temperature is high, then means more heat rejection will occur.
If the compressor discharge temperature is high, like because in a
So work will increase.
whole system we provide like insulator for insulating something we are providing. Let's suppose it is a polymer, and for that melting point of that polymer is close to 40, 45, 50, let's suppose 60, 70 degrees Celsius. Now if a compressor discharge temperature is of 70 or more than that, then it will try to melt down that system. So that's why we don't want the high compressor discharge temperature. If it is high, then we have to provide some cooling system like water cooling and some cooling, so we are going to provide them. So it's like we want compressor discharge temperature should be less.
Yes, sir.
Hmm. And then we don't want to our refrigerant should be toxic. It should not be toxic, and it should not be inflammable. Flammability should be less. Flammability should be less.
Sir, but flammability is flammability. How it should be less?
Uh, Actually, flammability means like it started to convert it into vapor, and some temperature would be here, right? Temperature is there, and now it becomes a vapor. Now let's suppose it's very high inflammable, but comparable to petrol or diesel, we can think. So there it can easily caught fire. If a fire would be there, then it would be very dangerous to install in factory and all. That's why we used to think of flammability should be less.
So here flammability corresponds to ability to automatically catch fire.
Flammability, like it should not be. We can think of flame. Some things like mm, mostly flame will occur due to conversion of that liquid to how fast it can convert to vapor. It depends on vapor pressure of those things, like that only. Like if easily it can convert to the vapor, and also it should have tendency to get fired up. If it like only converts to vapor, but it has no tendency to get fired, then it's also okay.
Means is it like flashpoint?
Mm. But like some refrigerants is having no tendency to get caught fire. Okay, so for those refrigerants it is not its flammability is less. Flammability means just to get ability to get caught fire at what is it can get fired up. It is the flammability.
Yes, sir.
Mhm. So now last is the like dielectric. Dielectric strength. So we want high dielectric strength or low? What is the dielectric?
Low, sir. Low, sir.
Why?
So dielectric means have tendency to like
Hmm.
throw up electron or like.
No, what is the dielectric strength meaning? Dielectric strength meaning is like up to what maximum strength it would not be. It's like atoms would not get polarized. So you don't want your system to get your refrigerant to get polarized and lose its functionality. Hmm. So dielectric strength we want high, right? Because there would be electric field, because anyhow there would be current flowing in the system. Getting or not?
Yes, sir.
Hmm.
It is most right.
So dielectric strength should be high.
It
So
is most important in the hermetically sealed compressor.
So
Sir,
yes.
means here dielectric strength corresponds to electrical conductivity.
No. Dielectric strength means like in like capacitors we would have seen like how dipoles are making there. Like suppose plus and minus. So plus will try to attract sorry minus here. One minute. Minus and here it will become plus. One dipole will create and here again minus plus. So this way, if dielectric strength would be more, then easily it won't happen. Easily, system will not get polarized. If it is not get polarized, then it will able to do functionality till the end.
And if get polarized, then
Then, whatever the like properties of your refrigerant would be there, that say it would get changed. Okay, so in the electric field, system will try to change its functionality. So that's why we want our dielectric strength should be more.
okay.
Mhm. Mm, okay. Now coming to the leak detection test. Because in our whole system refrigerant would be flowing, so for that four tests are there that we are going to mm, commonly uh, frequently we used to do in our system. One is the halide torch test, like it is also like for the matching type of questions more. uh, Halide torch test. So it is used for the first, here only two things you have to remember. Okay, it is one minute. It is used for freons. Freon refrigerant, we can use it, and it is done in wherever freon refrigerant we are using, there we will use this refrigerant, and bluish flame will come. This color and where we are going to use this test. Two things you have to remember only. Bluish flame will convert. Actually, generally it would be like bluish flame would be there, and it will if like a leak would be there, then bluish flame will convert to bluish green. Only this conversion you have to remember, and for what it is going to used, that you have to remember. And second test is like sulfur stick method or sulfur ribbon method. So it is used for only ammonia NH3 leakage. If anywhere we are going to use ammonia as a refrigerant, there we will use it. And what would be the working for that? Like if ammonia is leaking, then ammonia sulfur forms white fumes. So here white fumes would be there. White fumes of ammonium sulfide. Ammonia, and here we'll put ammonia and sulfur forms. Ammonia sulfur forms white fumes of ammonium sulfide. So here only for sulfur stick test would be used for ammonia leakage, And halide torch test used for freons, sulfide formula would be like NH4 2S. And last third one is the ammonia swab test. Ammonia swab test means for wherever ammonia is the refrigerant, we use sulfur stick method or sulfur ribbon method, and wherever we are using SO2 as refrigerant, then we use ammonia swab test. Means the same thing will happen here also. Hmm. So here what we use, a cloth dipped in ammonia and passed over the pipe where we are using this refrigerant. So same white fumes will form. Again, so white fumes would be of this only, because here also same combination is there. So it would be the same here also. Apart from ammonia leaking, here SO2 leaking it would be there. Last test is the soap bubble test.
Sir, please can you repeat that swab test?
Uh, Ammonia, like first second test for sulfur stick method or sulfur ribbon method, here it is for ammonia, and wherever in the pipe ammonia is leaking, then sulfur we use, and it forms the white fumes of ammonium sulfide. Here it ammonia swab test is for the sulfur dioxide, wherever we are using sulfur dioxide as a refrigerant. Then a cloth would be dipped in the ammonia. We that cloth will roam around the pipe, and if white fumes will be formed anywhere, then there from there um, uh, refrigerant would be leaking. So that white fumes of ammonia same as ammonium sulfide again. Got it? Hello.
Yes.
Uh, Last is the soap bubble test. Mm, Soap bubble test, it is used for hydrocarbons. So these four tests you just simply remember for what it is used, and just that is the enough. Okay. So like these four tests today I'm like covering whatever the here and there random things will come, so that we are covering. Okay. And now last is the ramming of air.
In soap bubble test, sir, can you explain again?
What?
Soap
In
bubble
soap
test.
bubble
So
test, like
how we perform, sir?
mm, actually here only I took this only, like for what it is used. Hmm. It is used for
For
hydrocarbon. Huh?
for hydrocarbon, it would be soluble in that soap bubble. So, in my opinion, that bubble doesn't form during that test, isn't it, sir?
Actually, I also took only working. It never in asked there. So there it so bubble test is used for which refrigerant. That only they are. So I took this line there from there. So bubble test
Yes, sir.
used for hydrocarbon. Huh.
This method is used in the automobile refrigeration system. In automobile, like cars, the soap bubble test is used for leakage of the refrigerant.
Okay. So like in automobiles, they would be using hydrocarbon as refrigerant. Might be there. Huh?
Yes, sir. R11348.
Mm-hmm. So here I'm just giving you these for the like for get objective type of questions. So I'm deeply theory. I also haven't studied for them. Huh? So it is not because if you are going for like conventional type, then it is required. For MCQ, you have to know what is the main thing is there, and that you know. Okay. So what we have covered. Okay. So ramming of air. So what is the meaning of ramming? Can anyone tell? Because for the it is related with the air refrigeration system. We have studied air refrigeration cycle, right?
Yes,
Hello.
sir.
Hmm. So like if we all the system inside air refrigeration cycle also we want like pressure should be more than the 1 atmospheric pressure. So what happens like when aeroplane or anything would go up, then pressure is reducing, keep on reducing. So let's suppose,
So circulating or throwing that air surrounding
what?
something. Ramming of air means circulating, like airflow creating or like that.
Also like when aircraft is running at like 1,000 kilometer per hour, right?
Mhm.
1,000 kilometer per hour. So whatever air would be for the cooling refrigeration system, it will come inside. What would be the velocity of that air? It would be very high, like same as the this plane velocity, right? Got it or not?
Yes, sir.
So we don't want this much high velocity that to come inside our components. So it might also damage them, and also this much energy is of no use if it is only velocity. So what we try to use, we want to convert this high velocity also for our purpose. Got it?
Like ambient pressure, right? So maintaining ambient pressure.
No, if it is something is coming inside the system, then ambient pressure, you
Mhm.
forget about ambient pressure. It will come with ambient pressure P naught, some temperature T naught, and this velocity V naught. This would be the initial condition of the air that would come inside the system. Okay. Now with we will condition this air, and then it will go to the compressor. Got it?
Huh.
Sir, means this is for open cycle.
It is for the Breton cycle, whatever we have saw there.
Joule cycle.
There, Joule cycle is open cycle, right?
Yes, sir.
So in like there we have saw it would in aircraft system we generally use open cycle only because there is no like redundant ample amount of outside air is present. So we take that air and condition it, and it will work. So here what we in ramming generally what we does, outside air will come inside the system, and its temperature would be of the like surrounding temperature, let's suppose T naught, and velocity would be let's suppose C naught, and the pressure is P naught. It is like outside condition. And now it is the supply to compressor. So here what will we do, here temperature and the pressure, let's suppose it is the zero condition and it is the first condition. This we don't know what would be this, and now we will put this C1 as 0. Like now this velocity is become velocity, we will like we will use this velocity to change this some conditions. So how can you do that? Can anyone like find here these conditions I will give, and velocity you have to make 0, and you have to find the P1 and T1. Got it? And let's suppose this system is the adiabatic, reversible adiabatic. So from 0 to 1 we suppose like it is reversible adiabatic. So uh, this way temperature will change, right? From it will come from 0 to T1, and P1 to P naught, gamma minus 1 over gamma. This would be the first relation here, and second energy balance we can make, right? So energy, what energy would be here, it would be like H naught plus C naught square by 2000 is equal to H1. If like they sometimes it will say it will 0, here velocity would be 0, or sometimes it will say some velocity they will give. If some velocity is given, then C1 square by 2000, and H naught and H1 you can write Cp T naught, Cp T1. So this would be the second equation. So two equations and two unknown you can easily find, right?
Mm-hmm.
So for this
Sir,
quickly,
what find
hello.
here means what to find?
What are you saying?
You told that here from two equations you can find here, but
This
what to find?
this P1 and T1
P2.
you don't know, na? Supply
Yes,
to
sir, final conditions.
this is like rammed air condition. We used to say rammed air condition.
And sir, which is the device?
Here, actually, we used to device name is also we don't know. We used to say like air is before going to compressor, air has been rammed. In questions like that, they used to say. So first you have to find the rammed air condition, and then also same question will extend to the our like air refrigeration system. There the condition after coming through this problem, those condition we have to use there because they are inlet to the here inlet to the compressor we they will give condition that condition will come from here and then same problem will proceed. We cannot use these conditions there. So they, generally it is so said like here nothing it is some sort of again diffuser type of thing is this, right? Diffuser
Yes, sir.
so we can say it is diffuser because in diffuser what happens, velocity decreases only, right?
Yes, sir. Pressure increase.
So that we can say it is diffuser. But in no problem they say they will say like a diffuser we have installed there. So we can think of like
So,
here velocity we have reduced. So in order to increase velocity we used to use nozzle, and here we will use diffuser.
so what is practical application of ramming in
So
aircraft system, sir?
Okay.
What if we are not using ramming?
so like
Then,
first of all like sharp if 1,000 kilometer or 12,000 kilometer uh, speed of this air will come and directly will come inside the our compressor. Hmm. So it might like break some parts there because it is very high impact loading would be there, and already like impact loading would be there. Then sometimes the air velocity would be here, and again direction will change. It will come here. So what will happen? Like sometimes load would be here, and then cyclic loading will come, and fatigue will also might come. So many problems will come with the high velocity of air. So in order to avoid all these things, we go for the like standard whatever speed would be required for the running the compressor that will use. So before that, if
okay, sir.
you can avoid that, then use that. Huh.
Sir, that kinetic energy we try to use as a pressure energy. Some pressure.
That also fine, huh? Because here kinetic energy you are going to use. Hmm.
Sir, here enthalpy is the function of internal energy and the flow.
What?
Enthalpy
Enthalpy
is a function of internal energy and flow.
is always na enthalpy we have defined as U plus P, and U is the like internal energy and it is flow work. So for the air open system anywhere we use always use the enthalpy only. So for this quickly we do one problem, and then we'll see next part. Mm. So here like you have to consider C1 as 0 and the mm, initial velocity C naught you have to consider as 800 kilometer per hour, and the ambient condition like T naught and the P naught. P naught is zero point 0.9 bar, and T naught is the 250 Kelvin. So you have to find the P1 and T1. So like that in words they might also say these things. So can you quickly like using these two equation P1 T1 can tell?
CP 1.005.
CP always for air, if anywhere mentioned, then CP would be 1.005. Anyone did?
Doing, sir.
यस सर 1.25 बार प्रेशर है और टेम्परेचर है 274.57.
Mhm. For this, first you have to do temperature direct. What anything you can find, right? From here, this equation you can find the pressure, right?
अब पहले टेम्परेचर फाइंड आउट करना होगा.
Temperature also you can find from here. Put this zero and condition only use temperature here and see. From this equation you can find the temperature and from this equation you can find the pressure, right?
Mhm.
So temperature would come 274, how much? 20.57, right? Here only I will write once. Uh, okay, first you find the temperature from here, then here put the temperature. Okay. So H naught would be 1.005 and the temperature T naught is the 250 plus this velocity is 8000 kilometer per hour. You have to convert that to meter per second, right? So how much this is coming?
222.2.
Okay, velocity you are telling 222 point.
Yes.
22.
Okay, so square of that 222.22 square divided by 2000 and is equal to 1.005 and t1 would be here. If some velocity like they want some velocity for the rammed air, then also same thing we can do. That velocity we'll put here and temperature from here we can find. Temperature will become 274.57 Kelvin, and now put here 274.57 divided by 250 is equal to P1 divided by 0.9 to the power 0.4 divided by 1.4. So whatever will come, it would be the P1 from here. So P1 will become how much? 1.25. Okay. So here like velocity of all this also can be given. So now 1 minute. Hmm. So now here coming to again like why I told like low specific heat would be required. 1 minute. Hmm. So here let's suppose some part of enthalpy is there. Okay, so let's suppose some heat delta H is there, that is going to convert M, C, P and delta T. Some delta T is there. Okay. Now let's suppose this Cp is high. Hmm. So what will happen with this M dot? For a given amount of heat, and this drop in temperature is also fixed because we are going to come from here to here only. Hmm. So if Cp is high, then what will happen with M dot?
Decrease.
It will be less. So it has been
Mm.
asked in only that context. Okay. So if like Cp would be high, then M dot of liquid would be less. So 1 minute. So what is the this dryness fraction? Mv divided by Mv plus Ml, right? Hello.
Yes, sir.
Now if let's suppose this mass of liquid would be less. Actually, what we want here, mass of liquid less or high for our purpose?
Yes,
Less.
sir.
High. We want high. So if mass of liquid becomes less, then dryness fraction will would be more, right? Hello.
Yes, sir.
If dryness fraction would be more, then what will happen with refrigeration effect? Let's suppose this high dryness fraction means here it will come. So refrigeration effect would be very less.
Very less, yes, sir.
So now refrigeration effect would be less. So if Cp would be high, then mass of liquid would be less. So dryness fraction would be high, and refrigeration effect would be less. So that's why we want low specific heat. Okay, is it clear?
Ah,
Hello.
yes,
Yes,
sir.
sir.
Okay. So I think
Sir,
hello.
means there
Your
are two
doubt is
specific
what, sir?
heat
What?
for liquid and vapor.
Mm-hmm.
So means we want this just now you told this for means liquid part,
Hmm.
and for vapor part it should be low high.
No, no, we are saying about this only here. Now specific it for specific for liquid. We have said here only.
For
Yes.
after compression,
You are saying about what would be specific it here. Huh?
for vapor refrigerant.
Sir, it means that specific heat for liquid should be low and specific heat for the vapor should be high.
But here high would be beneficial, right? For a liquid side, generally we have to you have to say about liquid. Here we don't go for specific. After that, latent would be high we want, and specific heat at the liquid side we want less, because there much loss is not there. But here loss in refrigeration effect would be very high. If here liquid side it would be somewhat more. So loss in the refrigeration effect would be very high. That's why we want less here. If here would be it would be somewhat lesser also, then work like functionality is there. But here, like if you lost your refrigeration effect by 40 or 50%, then it is of no use. Got it or not?
Yes.
So means like more it is important to be less here. That is more important. So one more thing I think is there. Hmm. Okay. Okay. So like for today, I think we should stop here.
please send a PPT, sir.
Okay, okay.
Sir,